A very good evening, everyone. I, Dr. Seema Verma, welcome you all to the fifth day of Atal Online FTP on recent trends in deep learning and large language models. Now, I welcome our guest speaker, Dr. Akansha Singh. Dr. Akansha Singh received her BTech and MTech degree in computer science and the PhD degree in image processing and machine learning from IIT Roorkee. Currently, she is professor with the School of Computer Science and Engineering, Bennett University, Greater Noida. She has also undertaken government-funded project as the principal investigator. Her research interests include image processing, remote sensing, IoT, and machine learning. She has served as an associate editor and a guest editor for several journals. Welcome, ma'am.
Thank you, Seema ma'am, for the introduction. A very good evening to all of you. Myself, Dr. Akansha Singh, and today I will be talking on recurrent neural networks and long short-term memory. So let me just share my screen so that we can quickly start. So I think my screen is visible to all.
Yes, ma'am.
Okay. So today we are going to talk about recurrent neural networks and long short-term memory, that is LSTM. So RNNs and LSTMs have been quite a hot topic these days. A lot of people have been talking about RNNs and LSTM. And when we talk of RNN and LSTM, these are different from the traditional neural networks that we have been studying, the traditional deep learning models that we have been studying, and they are different because they are used in some different applications. And based on that application, the architecture of these models differ for different kind of applications that we have. So whenever we hear the term RNN and LSTM, the first thing that comes to our mind is sequential data. And if I talk of sequential data refers to the data where the order of elements is important because the elements are dependent upon their position, their sequence, and it captures temporal or sequential relationship between data points, making the sequence of the data crucial for analysis or prediction. So whenever we are talking of sequential data is basically the data where the order of elements is very, very important. For example, if I speak a sentence and I want to say my name is Akansha, but in this case, if I use the same words, that is my name is and Akansha, and I talk something like this, name my Akansha is. So if I change the order of the data, the entire meaning of that particular statement is going to change. I'm going to lose the context in which I'm talking. So that is why we say that the order of the element is of great importance in sequential data. So whenever we talk of sequential data, one of the most common sequential data is the textual data that we talk of. So any text, any statement, any sentence, the order of the words is very, very important, and that kind of a data is called a sequential data. Also, sometimes you will see that the time of the data, that means the temporal relationship between the data. For example, if I want to see the growth of a particular company for the last 10 years, so that time sequence is important. Starting maybe from 2001, I want to go up to 2010. So if I change the order of that years, I will not get a time sequence data. So sequential data basically is a data where the order of elements is important and the data context of the data depends upon the position and the sequence in which that data has been used. So if we talk of the characteristics of sequential data, how we can say any data is sequential or not. So first thing is the order matters. That means the sequence in which data points appear impacts their interpretation. For example, in a sentence, the order of word affects the meaning. So in a sentence, if I change the order of words, the meaning of the sentence can change. Similarly, temporal dependency. So the current data point may depend on one or more previous data points. For example, if I want to predict the stock prices based on the past trend, so there also, the time is going to be crucial. We cannot change the order of time. We cannot say I'm going to see the stock price of 2010 first, then 2006, then 2001. So if I change that order, I won't be able to find the correct relationship or the correct trend in the data. So there are temporal dependencies also in the sequential data. Then variable length. So sequences can vary in length. A sentence can be of 2 words, a sentence can be of 5 words, a sentence can be of 20 words. So in sequential data, whenever we are talking of sequential data, the length is also variable in all the cases. So the types of sequential data that we have is time series data, like we talked about, the data recorded over regular intervals, time intervals, for example, stock prices over time, weather data where we have temperature over a day or humidity over the day, or we have a sequence of days and then we have to find out the trend, or the ECG signals in healthcare. So if you look at the ECG signals also, they are also kind of time series data because we are recording the ECG signal of a person over a period of time. Then text data, so a sequence of character or words, sentences in natural language processing, then DNA sequences. So all these are textual data which follow some sequence. Then audio data, a sequence of sound waves or spectrograms, for example, speech signal for speech recognition, music composition. So if we look at any audio data also, so the audio data also, the beats are going to follow a particular sequence. If I change the beats, the entire context is going to go away from that particular audio. So whenever we have to do audio processing, there also we need to use sequential data. Then the next type of data that we have is video data. So video data is again a sequence of frames over time. So we have images over a particular time, and when we create a sequence of these images, it becomes a video. So in videos also, if I change the order of the frames, suppose I have a order of frames which is 1 to 10 frames. And now if I change the order 10 to 1, then the entire video will be reversed. Or if I randomly change some of the values, then also the order is going to change. So examples of video data are action recognition, video classification. So anytime I'm doing any kind of action recognition or I'm doing any kind of video classification, in all the cases, I will be having a sequence of frames, and the video data is again an example of sequential data. So the applications of sequential data include natural language processing, where we are doing some text kind of processing, text generation, translation, and I'm doing some sentiment analysis. So in all these cases, we are using natural language processing, which is again a kind of sequential data. Then we have time series analysis, where we have stock market prediction, weather forecasting, and this sequential data is again the time series data where we are doing stock market prediction and weather forecasting. Then another application of sequential data is speech processing when we want to do some kind of voice recognition, we want to do some kind of text to speech synthesis. So in both the cases, we call it as a sequential data. Just give me 1 minute. There's some issue in my system. Just give me 1 minute. Okay. So the applications of sequential data include natural language processing, time series analysis, speech processing, healthcare, for example, analysis of ECG signals, EEG signals, and there are another application of sequential data is autonomous system, where we have traffic flow prediction, robot navigation. So in all these cases also we use sequential data. So for example, if I'm talking of traffic flow prediction, so again there, since we are following a flow, so there also the order of the data is going to matter, in which order the traffic is flowing, which vehicle is to be followed by which vehicle. So in all these cases, the sequential data is used. So whenever we talk of sequential data, the basic neural networks or the generalized deep learning neural networks that we have, they do not work well for sequential data. And why do they not work? Because all these CNNs, all the networks that we have, they are made up for some kind of independent data. So when we talk of sequential data, in sequential data, each of the input is dependent upon its previous input and the next input. So each of the input is not independent. Rather, the input is dependent upon the other inputs that are coming to the system. But if we talk of a CNN system, if I'm talking of a simple CNN, where I'm giving some images as input, so there the uh, uh, input is not dependent on the other image. So suppose I want to classify the images of cats and dogs. So if I'm giving an image of a cat and then again I'm giving an image of the cat or I'm giving an image of the dog, so that sequence is not going to matter the performance of the CNN because all the inputs are independent of each other. But when I'm talking of a sequential data, for example, if I want to make a text chatbot where I want that, okay, my chatbot should predict the next text that is coming. So if I'm giving a question to my chatbot, the order of the input is very, very important. Suppose I'm saying, how are you? So how are you? These three words are dependent on each other. If how comes before are, it should come before are only. If you comes after are, it has to come after you only. If I'm going to change the order, the entire context of my data is going to be moved away. So that is why to process these sequential data and to have applications related to sequential data, we have a different class of neural networks, and the most important out of them is the recurrent neural network, or we also call it as the RNN. So, a recurrent neural network basically imitates the function of a human brain in the fields of data science, AI, machine learning, and deep learning, allowing computer programs to recognize patterns and solve common issues. So, unlike traditional feed-forward neural networks, RNNs have recurrent connections, enabling them to retain information from the previous input through a hidden state. And this allows RNNs to model temporal dependencies in the data. So what additional we have in an RNN as compared to any other deep neural network is that in RNN we have recurrent connections. When I say recurrent connections, that means they're kind of feedback connections that are there. And with the help of these feedback connections, we are able to retain the information from the previous input also. So whenever I'm giving a sequential data to my network, there is a hidden state in my network which is going to keep the information of the previous state also. So this way it is able to capture what my previous data was, and since all the inputs are dependent upon each other, so that way we pass on the information of the previous input to the next input also. So that way we are able to um, put up the concept of temporal dependencies. That means we are trying to capture the sequence in the data by passing on the information of the first input, so maybe t minus 1 to t. So why we say RNN is special? Because first and foremost thing is that RNNs have internal memory. This is the key feature of RNN, and it allows them to remember past inputs and use that context when processing new information. So in all the RNNs that we have, there is an internal memory, and this internal memory is used for, storing the information about the past input. So we have the information about the past input, and whenever any new information is coming, we can pass on this information and how processing can be done when new information is coming to it. Then sequential data processing. So because of their memory, RNNs are exceptional at handling sequential data. So where the order of elements matter, this makes them ideal for speech recognition, machine translation, natural language processing, and text generation. So they are capable of doing sequential data processing because they have a memory. The memory has the data about the past information it has, And with the help of that past information, it is able to capture the idea of sequential data. And then, since it can have the information with it, it is also able to process the sequential data. Then RNNs are capable of contextual understandings. RNNs can analyze the current input in relation to what they have seen before. This contextual understanding is crucial for tasks where meaning depends on prior information. So RNNs are also able to handle the context related to data. So since they have the information about the past input, so they know what is the relationship of the current input with the past input. So we understand the context also. For example, if I'm talking about something, if you know what I have previously talked and what I'm talking now, so you will be able to find out what is the context. And according to that context only, you are going to give me an answer. So the same thing happens with the machine also. In the machine also, we have the contextual understanding. The RNNs have a contextual understanding. They have the information about the previous data. They have the information about the past data. And based on that information, they understand the context, and that helps the machine to respond better whenever any input is coming to it. Then dynamic processing. So RNNs can continuously update their internal memory as the new data is going to come and they're going to process the new data. The memory is also each time updated. This helps them to adapt to changing patterns within a sequence. So whenever we have a sequence, as my model is going to train and new input is going to come, the internal memory also gets updated each and every time. So with the updation of this internal memory, my RNN will be able to process the data properly. So if we talk of RNN, so if you look at the image over here, this image, the first image on the left is an image of a simple deep network. Maybe it has an input layer, then it might have multiple hidden layers and the output layer. But if I rotate this entire thing in anti-clockwise direction, so I make a model for a recurrent neural network. So over here, if you see, I'm giving multiple inputs at the same time, and each of the input is independent of each other. But in case of recurrent neural network, you see, we have just rotated the entire network into anti-clockwise direction. And when we convert it into an anti-clockwise direction, we can see that we have an input at point B, then there is a hidden state H at point C, and then there is an output A. So instead of going linearly, the recurrent neural network is going to work vertically. And now you can see there is a recurrent connection also. That means there is a loop on the node H. So that recurrent um, connection shows that there is a feedback mechanism, or we can say that the past memory is being stored over here. So all of the inputs and outputs in a standard neural network are independent of one another. However, in some circumstances, such as when predicting the next word of a phrase, the prior words are necessary. And so the previous words must be remembered. So suppose I'm doing some text prediction or I'm generating some text. So in that case, if I have to generate the next text, I must know that what was the context of the previous text, what was generated, and now what should be the next thing. So for that, I need to know about the past information. And if I know about the past information, so I will be able to better answer these questions. As a result, RNN was created, which used a hidden layer to overcome the problem. And the most important component of RNN is the hidden state, which remembers specific information about a sequence. So we can see that sorry, the RNN has a hidden state, and this hidden state stores the information which can be used for the next state in a sequence. So, if we talk of the architecture of RNN, the RNN architecture comprises of an input layer. So, this layer receives the initial element of the data. For example, in a sentence, it might receive the first word as a vector representation. Then we have a hidden layer, which is the heart of the RNN, and the hidden layer contains a set of interconnected neurons. Each neuron processes the current input along with the information from the previous hidden layer space. This state captures the network's memory of past inputs, allowing it to understand the current element in the context. So, whenever we are talking of the hidden layer is the most important layer in the entire RNN architecture, and the hidden layer comprises of the neuron, and it processes the current input along with the information from the previous hidden layers state. And the state captures the network's memory of past input. So whenever we are talking of state, that state basically refers to the past data, that what was the information that we have from the past input. So that is what a state is there. Then the next important part of the architecture of RNN is the activation function. So the activation function introduces non-linearity into the network, enabling it to learn complex patterns. It transforms the combined input from the current input layer and the previous hidden layer state before passing it on, right? So what activation function is that? Thus, the objective of activation function is also same in RNN as in any other deep network. So the activation function is used basically for introducing non-linearity into the function. So whenever we pass on any data to the activation function, it is going to find out whether the neuron should be fired or not, and it transforms the combined input from the current input layer and the previous hidden layer store before passing it on. So it transforms the input for passing it on to the next layer. Then we have the output layer. So the output layer generates the network's prediction based on the processed information. In a language model, it might predict the next word in the sequence. So output layer basically helps you to generate the network's prediction. Whatever prediction is to be done is done through the output layer. So initially we have an input layer which is able to handle sequence data. This input layer is going to pass on information to the hidden layer. The hidden layer is the important part, which is going to store the information of the previous inputs also. Then we have the activation function, which is going to bring non-linearity into the network. And then we have the output layer, which is going to generate the network prediction or output. And also there is an important key distinction in RNN, which is the recurrent connection. So the recurrent connection within the hidden layer allows the network to pass the hidden state information to the next time step. And it's like passing a baton in the relay race, carrying information about previous input forward. So the objective of recurrent connection is to pass on the information to the next layer. So in the most simplest form of RNN, which we call a vanilla RNN, the network is just a single hidden state H where we use a recurrence formula that basically tells us how we should update our hidden state H as a function of previous hidden state HT minus 1 and the current input XT. So the most simplest form of RNN is this network that we see over here, which is also called a one-to-one network. So in a one-to-one network, which is also called the vanilla neural network, in a vanilla neural network, we have an input xt, we have a hidden state ht minus 1, and we have an output yt. So this is a one-to-one RNN where we just have one input at a time, which goes on to the hidden layer. The hidden layer will store the information about it, pass it on to yt, and whenever the next input xt plus 1 will come, it will have the hidden information also about the previous information. So this is the most simplest and basic form of RNN where we just have one-to-one connections, one input layer, one hidden layer, and one output layer. So generally one-to-one we do not use because it is of no use to us, but we have another one which is called one-to-many. And one-to-many is used in image captioning where we give an image and then based on that image, a sequence of words is generated. So if you look at one-to-many, a single input in a one-to-many network might result in numerous outputs. One-to-many networks are used in music production, for example, image captioning. So if you see over here, in one-to-many, I'm giving one input, but that one input has been passed on to three hidden layers. And then instead of having just one output, I can have three outputs also. So for example, in image captioning, if I'm giving an input as an image, so the output is a caption which could be more than one word. So this is an example of image captioning. Then we have another type of recurrent neural network, which is many to one. and we also have many to many. So when we have many to one, in that case, you can see there are multiple inputs over here. So if you see over here, there are multiple inputs over here, and we have only one output, right? So the inputs, if you see, there are more than one input. In one to one, we just have one input and we have one output. In one to many, we have one input, but we have many outputs. In many to one, it is just the reverse of one to many. We have many inputs, but we have only one output. And many to one is a single output that combines input from distinct time steps. So basically, we have given input from different times, and based on those different times, now I have one output. So sentiment analysis, emotion identification, all these kinds of applications, they use many to one. Then we have many to many, where for many to there are numerous options. Two inputs yield three outputs. Machine translation systems such as English to French or vice versa translation. So many to many, in many to many, we will have. So if you look over here, this is the complete. Over here, I can see one input, one output, which is one to one. Then I have one input and I have many outputs. So this is one to many. Then I have many inputs and just one output, which is many to one. Then I have many inputs and I have many outputs. So this is many to many. So one to one we rarely use, but one to many when I'm talking, the example could be music generation, image captioning, all these type of networks use one to many. When I'm talking of many to one, so in many to one, I can have sentiment classification, emotion classification, all these kind of problems use many to one sequences. And when I'm talking of many to many, so this is used for machine translation. For example, if I have a English to French translation, I can use many to many in that case. So I may give a sentence and the output will again be a sentence. So I'm giving a sentence in English and the output that I'm getting is another sentence in English itself. So many to many is used in different ways. For example, over here you see many in many to many, I'm giving three inputs. I have more hidden layers and I have three outputs. Whereas I can have a many to many like this also. I have three inputs and I have three hidden layers and I have three outputs also. So for example, in this case, we can do video classification. So in video classification, we use this kind of network. So if we look at a recurrent neural network, let's see how it works. So you have an input X, you have an RNN over here, the network, which has a recurrent connection, and you have the output Y. So the key idea is that RNNs have an internal state that is updated as a sequence and it is processed. So basically, when we talk of an RNN, it does not have a single block like this, rather it has multiple blocks. So whenever we are giving any input, how it is going to work? Suppose I am saying that the length of my input is t. So in this case, how this is going to work? Suppose I am saying x1, x2, x3, and up to xt. So all the inputs are going to go into this RNN. Now the first input is going to go over here. Whatever output is generated, the past information is passed on to the next sequence. Now when x2 will come, it knows the information what was there in the previous input because it has a connection over here. So this arrow that you see, which we have made in a feedback manner, in a loop manner, I have just unrolled it. So to show you that how the sequence is going to go further. So now in this case, when x1 is going to come inside, it goes over here, whatever information is being saved, and that information is passed on to the next sequence. Now this x2 will go over here. Again, some information will be created of the activation function, whatever weight we get, whatever hidden data we have, that will pass on to the next one. Now again, x3 will be processed along with the x3. Past information will also be covered, and we will move on to the next one. So this is how so this information is basically going over here also. Then this goes over here. This goes over here. So like this, we are following a sequence where each of the input knows the information about its past input. And this way the sequential data handling will be done and the sequential data will also be processed in a proper manner. So when we talk of RNN hidden state update, we can process a sequence of vectors X by applying a recurrence formula at every time step. So if we have whenever we are calculating a new state ht, there is some function that depends upon in our network what function we are using, which has some parameters w. So in this, we pass on the ht minus 1, that is the old state, and the input vector at some time step xt. So this ht minus 1 comes from the input xt minus 1. So the previous input state is passed on to the next state, and this new state is updated every time. And where it is stored in the memory which the RNN has. So all the RNN has a memory cell that we talked of, and in that memory we stored the information of the previous state, and this is how the function is going to work. So we can process of sequence of vector x by applying recurrence formula at every time step. So this is the output yt, which is a function of h and y, and this is the new state. So for calculating the new state, first we have to take into picture ht minus 1, that is the previous state, along with the input, current input. Once we calculate ht, this ht is used to calculate yt, which is the output. So yt is equal to f of why, which is another function with parameters w naught, and in this we pass on the new state ht. So we can process a sequence of vectors x by applying reference formula at every time step. So this is how the output is generation, and this is how the hidden state is updated. So hidden state is also updated after each step, and the output is generated using that hidden state. In the next time, this ht will become ht minus 1, and it will be passed on to the next input. So if we look at the recurrent neural network, initially we have the input x1 and the state h naught, that means the initial state. It goes into RNN. Whatever mathematical calculations we will do, we will apply ht minus 1 formula, and we have h1 with us. This h1 will pass on to the next one. The output will be generated using this, and this will further pass on. And now we have h2. When this is calculated, we have h3, and like this sequence is going to go on. And if you look at this, the input is also going in vertical order. That means like this, parallelly. And sorry, the input is also going sequentially. If it would be a normal network, so suppose in a normal network, how it will go, we will have the input like this, maybe over here x1, x2, and similarly this could be x3. So over here, if you see, the input will go like this in horizontal manner, and then we will have some nodes over here and some output over here. But in this case, we have simply turned it in anti-clockwise direction. So we have turned it like this, and now we have the input like this in this manner, x1, x2, and x3. So we can process of sequence of vectors by applying the recurrence formula ht is equal to fw ht minus 1 comma xt. So the same function and the same set of parameters are used at every step. So if you look at this function, which is fw, and this is the hidden state, so we are using the same formula at all the layers. It is not that we are using different for different layers. It is same for all the layers, because we have to do the same kind of processing on each input that we are getting. So if we talk of the vanilla recurrent neural network, that was the basic neural network. The state consists of a single hidden vector h. So we calculate ht is equal to fw, which is a function of ht minus 1 and xt. And this fw, we can use the function tan h over here. So we are using the activation function as tan h, and this is WHH into HT minus 1. So where this WHH basically means the weight at the hidden state, and into ht minus 1, which is the previous input, and wxh is the weight of x at h, and we are multiplying it by xt, and we get the final output as yt is equal to why into ht. So sometimes we call the vanilla RNN as an Elman RNN also, which is named after Professor Jeffrey Elman. So if we look at the RNN computational graph, how it works. So initially we have H naught, we have a function over here, x1. So this function is going to take two inputs, H naught and x1, and it is going to generate the output H1. Similarly, this h1 will again go to the same function. So important thing is that the function that we are using over here, the same function is being used over here also. The same set of function is used across all the layers. Now x2 is being passed on and h1 in this function, and I calculate h2. Once I calculate h2, again the same function is passed over here, and now I have h2 and x3 as input, and I get the output as h3. When I have this, similarly, this process will go on up to ht, whatever is the length of my input sequence. So if I'm taking the length of my input sequence as 5, in the first time I will have x1, x2, x3, x4, x5. So if we see, we are reusing the same weight matrix also at every time step. So this W weight matrix remains the same. Whatever in our neural network we have calculated the W, it will be used here also, it will be used here also, it will be used over here also. So in all the cases, the function and the weight matrix remain same at every time step. That means we are applying the same weights to all the inputs in our network. Similarly, if I have many to many, in many to many also the same weight function will be given. And if you see over here, every time I have multiple inputs and I have multiple outputs. Whereas in this case, if you see, there was a single input and a single output. And now in many to many also, you have a weight function, weight matrix. The same weight matrix is being used at all the layers, and we are giving the inputs over here, and we are getting many outputs over here. So when we are talking of many to many, in all the many to many, we have y1, l1, that is the prediction that we are having. Similarly, y2 will give l2, y3, l3, and yt, lt. And when all these combine to form the output L, which is a combination of L1, L2, L3, and LT. When we are talking of many to one, in many to one, again you see we have an initial state of hidden state H naught. X1 is going to go over here, and then we have FW coming into it, the function, and we have the weight matrix over here, and then we find out H1. Once we calculate H1, it is passed on to the FW, X2, and the same weight matrix is also being used over here. So we calculate H2 over here. Once this H2 is calculated, it will propagate forward, and like this only we will keep on calculating the inputs, and finally we have the output Y. And when we have many to one, so now in this case, you can see we are giving one single input. It is being calculated by FW. H1 goes over here. Now we do not have any more inputs. Only one input I had. And based on that one input, we have calculated multiple outputs. So this is an example, could be of image captioning and other such problems where we have just one input, but the output has multiple values. So, since in our network, if we are saying that we are having one to many, so I'm giving one input, but according to the network, there is also over here. So, what will be there? We put zeros over there so that no input is going over here. Or what we can do is you have y1, so you pass on y1 over here. You have y2, you pass on y2 over here. You have y3, you pass on y3 over here. So whenever we're doing a sequence to sequence, that means sequence to sequence is basically many to one and one to many. So we encode the input sequence in a single vector, like this. Suppose I have an input vector, I will convert it into a sequence x1, x2, x3. And I have a weight matrix W1. So that W1 passes x1, x2, and x3. And when we have to produce output sequence from in a single input vector, we find the output by passing on this W2, which is another weight matrix, and it gives the output Y1 and Y2. So let's see an example where we are doing a character level language model. So suppose my vocabulary is HELO and example training sequence is hello. So how hello passed on? Since I have the length of my vocabulary is 4. So this word that I want to pass, HELO, one character at a time. So X1 will have H, X2 will have E over here, X3 will have L, and X4 will also have L. And this input layer that you see, that means this is the first node, this is the second, so we have put one over here, this one is third, so this is the third one over here, and this is how it goes. So others are 0. So now when this will be passed on to the hidden layer, so hidden layer might be having some weights based on that there must be some hidden state. So how do we calculate it? We calculate it using the function tan h, whh into ht minus 1 plus wxh into xt. So this is the input layer, this is the hidden layer, and the values are going over here. So this value is going to go over here and doing some conversions. We get these weights. These are multiplied over here. For this, I get this value, and like this by calculating the function. And in the output layer, what do I get? I get 2.2 minus 1, 1.9, 2.2. So now we see that the input characters which were passed, H, E, L, L, and this was the hidden layer, and then the tanh function is applied. So we get the target variables, so target characters over here, E, L, L, O. So that is decided based on the weights that we have. So when I'm passing at least at test time sample characters one at a time. So suppose I'm passing H, it will go like this. Then whatever value of E has come over here, it will be passed on over here. Just a minute. Right, so how actually it works? First, we are giving the input character H, and all these values that you are seeing, they are a part of, by applying vectorization and other things, we have converted H into some embeddings. So these are the weights of the hidden layer. These weights of the hidden layer are multiplied. We get the output layer. Softmax function is applied. And when softmax function is applied, you see 0.84 is the maximum value. So that means we say that this belongs to E. So that is why we are getting an output as E. Now again, this E will be passed on in the hidden state. So it will come over here and the next values are calculated. So again, there is a this thing hidden state that we have. From this hidden state, we multiply and we apply softmax function. And again, we see that 0.50 is the maximum value in softmax. So this is assigned as L, or this is predicted as L. Now this input will pass on to the next one. So again, it will go to next one, L, and we are getting L. And again, this goes over here, O. So if you look at this H, automatically it has predicted that after H, E will come, after E, L will come, after this L, again an L will come, and then after L, O will come. So since I am using sequential data, so this is how the entire thing works. For first input character, everything will be calculated, it will be passed on to the next layer, and similarly, we will be moving on to the sequence. So since we have taken over here the size of my input was 4, so at one time I was able to give only 4 characters. So how this is done? We have a weight matrix W11, W12, W13, and for the first input, if you see 1, 0, 0, 0. So we get the weights as W11, W21, W31. And this weight matrix remains same in all the cases. In all the nodes, we are giving this same weight matrix, and it is being multiplied. We get this. So this is my matrix. This gets multiplied with the weight matrix, and I get this as the values of the hidden layer. And then using softmax function, I get this. So matrix multiply with one hot vector just extracts a column from the weight matrix. We often put a separate embedding layer between input and hidden layer. So this is embedding that is being done. So if we look at the advantages of RNN, it can process any length of input. Computation for step T can use information from many steps back. Model size does not increase for longer input. We can use the same model size. Same weights applied on every time step, so there is a symmetry in how inputs are processed. And if we talk of the disadvantages, the recurrent computation is slow. In practice, it is difficult to access information from many steps back. So one of the examples where RNN is being used is image captioning. So if you look at image captioning, in the input, we have given an image. And from this image, my CNN is going to identify the objects what are there. So it has identified a straw hat. So that straw hat has been passed on to an RNN. And based on that, it is going to predict the next word. So you see, we first use an image. That image passes through a CNN. The CNN gives us two classes of objects which it has identified as straw and hat. So this is straw hat is passed on to RNN, and my RNN is going to compute the further output. So it can give a caption that a man is wearing a straw hat or something like that. So what does the convolutional neural network will do? It is going to identify the objects. So for example, this is a test. So we have trained our model using all these kinds of images. Now, if this is the test image, so the image will pass on in the CNN. And instead of in the end using the softmax and FCC in the end, we use an RNN. So whatever values we get, the weight function is passed on to the hidden layer. And before we had the function h is equal to tan h, wxh into x plus whh. Now we will have the input of the hidden layer also. So whatever sample we are giving, the output came as a straw. Then that straw is passed on further. Again, it is passed on to the next sample, which is hat. And then hat is passed on to the RNN network. And the sample and token, that is we finish because only two things are given, straw hat. So from this image, I get the caption straw hat. So this is how so in this case, if you see there is one input, but there are two output, y1 and y2, which are straw and hat. So some of the image captioning example results could be, for example, if I give this image, my RNN can predict a cat sitting on a suitcase on the floor. Then a cat is sitting on a tree branch. A dog is running in the grass with frisbee. So how all this is happening? I gave this image to my CNN. It identified there is grass, there is frisbee, there is a dog. Dog is in a running position. So automatically it has generated a caption that a dog is running in the grass with a frisbee. Similarly, a white teddy bear sitting in the grass, a tennis player in action on the court, two people walking on the beach with surfboards, two giraffes standing in a grassy field, a man riding a dirt bike on a dirt track. So all this depends how well you are going to generate your captions. So these captions are generated using the Neural Talk 2 network, and all images have been taken from CCO public domain. So there's a Neural Talk 2 network, which is kind of an application where if you give the image, it is going to give you the caption for that particular image. So image captions can be wrong also. For example, if I show this image, the caption that is generated is a woman is holding a cat in her hand. So why? Because you can see a cat-like structure over here. So my CNN is not able to identify it properly. And whatever sequence of words it has given, based on that, the RNN has predicted that a woman is holding a cat in her hand. So in this case, this is a wrong captioning. A person holding a computer mouse on a desk. So instead of phone, it is imagining it to be a computer mouse. So again, this is a kind of wrong image captioning. A woman standing on a beach holding a surfboard. So again, this is a wrong or a failure case. A bird is perched on a tree branch. A man in a baseball uniform throwing a ball. However, he's catching the ball. So that kind of failure cases are also there. Now, once we talk about RNNs, there is another network which is a type of RNN only, but it has some other properties and it is useful in some other manners. So, which is called LSTM, and it is also the full form for LSTM is long short term memory network. So LSTM networks are again a type of recurrent neural networks and they are also used for sequential data and they're specifically designed to address the challenges of learning long-term dependencies in the sequential data. That means like we have seen in RNN, if we want to go back uh, four, five, if there's a small dependency, that means the context statements or the sequential data is small. In that case, RNN works quite well because each time we are just thinking about the past input. So whatever hidden state we had in the RNN can store the information of the previous input only. So that means it has short dependency. That means just before the input I have xt, it can know about xt minus 1. But sometimes in sequential data, we want to address long-term dependency also. So if I'm talking of xt, I want to know what was there in xt minus 10 or xt minus 5. So that kind of a thing is called a long-term dependency. So whenever we have these kind of long-term dependencies in sequential data, their RNN sometimes does not work that well. Rather, what we have to do is we have to use another network which is called long short-term memory. So if you see the name of the network itself is long, which represents long dependency, and then short-term. That means for some time it is going to hold, and then as the network will move on, it is going to remove. So the LSTMs overcome the vanishing gradient problem that limits the effectiveness of traditional RNNs. So vanishing gradient problem, I think all of you must be knowing. I'll quickly give you a recap of what vanishing gradient problem is. So vanishing gradient problem is when you are finding out the loss of the function or you are finding out the gradient after a point of time that reduces to a much higher length, and with the help of that it is called vanishing gradient problem. So we the difference in the changes we are unable to notice, and that because of that the training is not completed. So LSTMs overcome the vanishing gradient problem and which limits the effectiveness of in traditional RNNs. So traditional RNNs face vanishing gradient problem, but LSTM is capable of overcoming this particular problem. If we talk of LSTM architecture, the LSTM architecture is a bit different from RNN. In RNN, we had just one memory cell, whereas in LSTM, we have a complete architecture which involves the memory cell, which is controlled by three gates. So instead of one, we have a memory cell over here, which is controlled by three gates. And these gates are called the input gate, the forget gate, and the output gate. So these gates decide what information to add on, to remove from, and output from the memory cell. So like in RNN, we had a single memory cell, and using that memory cell, every time it was decided that okay, I will keep a hidden space with me, a hidden state with me, and whenever I move on forward, this hidden state will be passed on to the next input. Now in LSTM, we have an option where we have a memory cell which is divided into three parts: forget gate, input gate, and the output gate. And these three gates basically decide that which information should move forward, which information should stay back, and which information I should forget. So the input gate controls what information is added to the memory cell. So whenever I'm getting a sequence of data, the input gate is going to control that, okay, this information should be added to the memory cell or not. It will decide whether this is an important information or not. If it feels it is an important information, that information will be added to the memory cell. Next comes the forget gate. So whatever input gate is sending, the forget gate is again going to check and it will check whether this information should be kept in the memory cell or it should be removed. So if the forget gate finds that the information is irrelevant or insignificant, it is going to remove that information. Otherwise that information will remain in the memory cell. And the output gate controls what information is output from the memory cell. So once we have the information, now the output gate will control that whether this information should be moved forward to the next input or not. So a combination of three gates is over here, and with the help of these gates, my LSTM can, selectively retain or discard information. It can select which information is to be kept, which information is to be removed from my cell. So initially, whenever there is an input sequential data is there, and the input comes, the input gate comes in charge. It checks whether this information should be stored or not. If that information is to be stored, the input gate will store it. Now again, the forget gate will check whether I should remember this information or I should forget this information. That is why there is a name forget gate. So if it feels that the information is insignificant and unnecessarily I should not fill up the memory space, that information will be removed. Then once that selected information is passed on further, the output gate again selects whether this information I should send as an output or it is not required. So all these three gates have their own roles to take the input, to forget, and to output. And based on these three selection, the LSTM is able to selectively retain or discard information. So if we look at the LSTM memory cell, there are three parts as you can see, 1, 2, and 3. So this is 1, 2, and 3. So the first part is the forget irrelevant information part. This is the input gate which adds or updates new information, and this is the pass on the updated information. So first one is the forget gate which forgets irrelevant information. Then we have the input gate which adds or updates new information, and we have the output gate which passes the updated information. So if we talk of the forget gate is something like this, where we have the input xt coming over here, ht minus 1. This is the sigma is the function that we have, and ft is the function output, and this goes into x. So the information that is no longer useful to the cell state is removed with the forget gate. Two inputs xt, input at a particular time, and ht minus 1, previous cell output, are fed to the gate and multiplied with the weight matrices followed by the addition of bias. The resultant is passed through an activation function which gives a binary output. If for a particular cell state the output is 0, the piece of information is forgetted, and for output 1, the information is retained for future use. So basically what happens is whenever we are talking of the forget gate, xt and ht minus 1 is passed on. Again, it is multiplied by the weight matrix, and we have a function ft over here. This function is calculated, and if we get the output of ft is 0, that means this information is not important. If I get the value of ft is 1, this means that the information is important and it is retained. If I get a 0, the information is discarded. If I get a 1, then the information is retained. Then we have the input gate. So this is the input gate that we have. The addition of useful information to the cell state is done by the input gate. First, the information is regulated using the sigmoid function and filter the values to be remembered, similar to the forget gate using inputs xt minus 1 and xt. So initially we see that a sigmoid function is used, and the inputs ht minus 1 and xt are passed on to the input gate. Then a vector is created using the tanh function. So we have the tanh function over here which is used, which gives an output from -1 to +1, which contains all the possible values of from ht minus 1 and xt. And at last, the values of the vector and the regulated values are multiplied to obtain the useful information. So this tanh function is used because it is going to give all the possible values of ht minus 1 and xt. And this is the input gate, so all relevant information is passed from here. Then the forget gate filters this information, that which one is to be kept and which one is to be discarded. Then finally the output gate. The task of extracting useful information from the current cell state to be presented as output is done by the output gate. First, a vector is generated by applying tanh function on the cell. Then the information is regulated using the sigmoid function and filter by the values to be remembered using inputs ht-1 and xt. And at last, the values of the vector and the regulated values are multiplied to be sent as an output and input to the next cell. So the output gate, whatever it gets from the forget gate, again tanh function is used over here, and the information is regulated using the sigmoid function. And then at last, all the values of the vector and the regulated values are multiplied so that we know what is to be sent to the output and what is to be removed. So why do we want to use LSTMs? So if we talk of LSTMs, RNN struggles with long-term dependencies because gradients diminish or grow excessively during back propagation through time. So in RNN, what happens is when we are finding out the gradient of the training, that means when we are doing the gradient of the function while training, either there is vanishing gradient problem, that means the gradient becomes so low that we are unable to find the change and the weights are not updated anymore during the training, or they explode. So when they explode also, then also the network is unable to converge because of the exploding gradients. So these two problems occur whenever there is long-term dependency. So what LSTMs do, they are designed to selectively retain relevant information, making them effective for tasks requiring memory over long sequences. So whenever there are long sequences, LSTMs are best used and we are able to overcome the problem that are there with RNNs. LSTMs overcome all these problems. So if we have a quick comparison between RNN and LSTM, so or they differ in different aspects. So we will see what are these different aspects in which these RNN and LSTM differ. So if I talk of the architecture, there in RNN there is a simple structure with a single hidden state. We have only one HT unit that we have. But when we talk of LSTM, in LSTM it includes memory cells and gating mechanisms, which include the forget gate, the input gate, and the output gate. If I talk of handling long-term dependencies, so RNN struggles with long-term dependencies due to vanishing gradients, whereas LSTMs are effective in handling long-term dependencies using memory cells. Vanishing gradient problem, if we talk of, so in RNNs, they are more prone to vanishing gradient during backpropagation, whereas in LSTM, they are designed to mitigate the vanishing gradient problem. So the LSTMs are able to easily mitigate vanishing gradient problem and they do not suffer from the vanishing gradient problem. If we talk of the training complexity, the RNNs are relatively simple and faster to train, whereas if I talk of an LSTM, it is more complex and slower to train due to additional computations. Because in LSTM, in RNN, we just have a single memory cell, and over there the hidden state is stored. Whereas when we come to LSTM, the complexity increases because we have additional computation. So we first have to calculate the input for the input gate. Then we talk about the forget gate where different information is to be calculated. And then in the output gate, again, we have to calculate the thing. So instead of one, we are doing three computations over here. So that is why LSTMs are more complex and they are slower to train. If we talk of the applications, RNNs are suitable for short-term dependency, example basic sentiment analysis. But if I talk of LSTM, it is suitable for tasks requiring long-term memory. For example, text generation, machine translation, video sequencing, in all these kind of things, we require LSTM. The memory capability. RNNs have limited memory and only remembers the recent inputs, whereas in LSTM we have an enhanced memory with selective retention and forgetting of information. So we have a more enhanced memory version in LSTM. The parameters in RNN are fewer parameters due to simple architecture, whereas in LSTM there are more parameters due to additional gates and memory cells. Sequence length, RNN struggles with long sequence due to gradient issues, whereas LSTM requires a LSTM has superior performance for complex sequential tasks. If we talk of the use cases, the basic sequence modeling like time series forecasting can be done using RNN. But if we talk of advanced sequence modeling, in that case, speech recognition, machine translation, for all these kinds of applications, we can use LSTM. Now, once we know about RNN and LSTM, when if I want to apply RNN and LSTM, so they can be easily implemented in Python. In Python, using transformers and keras, you can implement RNN and LSTM. They are already available in Python. There are simple commands that you have to use. Then, based on your application, you can extend it further. So, I will quickly show you the basic implementation of RNN and LSTM in Python. So let me reshare my screen so that I can show you the code also. Okay, so I think my screen is visible. Yeah. Okay. So if I want to do RNN and LSTM implementation in Python, we can use the TensorFlow and Keras for a sequence classification task. So in case if you do not have TensorFlow, you have to simply write pip install TensorFlow. So if I write this pip install TensorFlow, it is going to install TensorFlow into my uh, Python notebook. Then I'm importing NumPy as NP because I want to use some arrays and other things. Now in TensorFlow, we have tensorflow.keras.models. So from there, I'm going to import sequential. So using this sequential, I can add sequential layers and a sequential model can be created. And from tensorflow.keras.layers, I'm going to import simple RNN, LSTM, dense, and embedding. So if we see this LSTM is already there in the TensorFlow Keras layers, you can use this LSTM network directly. Then this is a basic implementation based on your application, based on your requirement. You can customize the model anytime. And this is a simple RNN where a simple RNN vanilla network is being used. So we are generating some synthetic sequential data. So suppose I have taken the vocabulary size is 100, sequence length is 10. That means every time I will give 10 input at a time. And the number of samples is 1000 because I have taken 100 into 10, which is 1000. So number of samples is 1000. Then I'm randomly generating some input sequence and binary labels. So there is X and Y. I have the generating some random data. So using numpy np.random, random integer 0 to 100 and size is equal to 1000 comma sequence length. So I'm just creating some input. Similarly, Y also I have created like this for binary classification 0 or 1. So I am classifying any input which is coming. I am just classifying into two classes, either 0 or 1. Then I've split the data into training and testing. So zero point 0.8, that means 80 is to 20, I have split into training and testing. And I've created the X train and X test by taking the train size of X and Y as the train size. Now to build a simple RNN model. So if I want to create a simple RNN model, I can simply say RNN underscore model, that is the name that I'm taking, and then I'm using a sequential model. So whatever we have imported from Keras, we are using sequential. Then I'm giving the embedding there where I'm saying that the input dimension is vocabulary size, the output dimension is 32, the input length is the sequence length. Then I'm adding simple RNN, which is my simple RNN network, 32 and return sequence is equal to false. And then I'm adding a dense layer. which is the and using the activation function sigmoid. So this is the output layer. So this is a simple RNN that I have made. Then I will write RNN model dot compile and optimizer. I'm using Adam. Binary cross entropy is my loss function, and I'm using the accuracy matrix. And then I will write RNN underscore model dot fit. So I'm going to basically train my model. And over here I've given 5 epochs. And then to evaluate the RNN model, I will print the RNN loss and RNN accuracy. So this is how a simple RNN can be created. Now this train and testing data, I have just generated some random data. If you are doing some actual training and you are applying it on a problem, you can use your own training and testing data, read it from CSV files, and you can do it. So when I'm going to run, it will say training a simple RNN model, and it shows RNN test loss is 0.84 and test accuracy is 53.50. So because we have just run it for 5 epochs, so I'm getting a low accuracy. Similarly, if I want to build a LSTM model, again, you can see I'm using the sequential model. Embedding is same. Instead of simple RNN, I will write LSTM over here. So I will create a LSTM network. And then dense layer I'm adding, and LSTM model dot compile, LSTM model dot fit, and again I'm evaluating the LSTM model. So if I see the accuracy of LSTM model is 46, again because I have just run it for 5 sequence on some small data set. If I want to make predictions, I can make predictions also. So some random text sequence I have generated again using NumPy, and to predict, I can use RNN underscore model dot predict, and I'm printing if the input I'm getting is greater than zero point 0.5, it will predict positive, otherwise it will predict negative because I have two classes, 0 and 1. So for 0, I'm saying it is negative class. For 1, I'm saying it is positive class. Similarly, if I want to do LSTM prediction, I can write LSTM underscore model dot predict, and the same thing I'm doing over here. And it shows me the output. So it shows me RNN prediction is negative and LSTM prediction is positive. So since we have not trained the model properly and it is just a random data, so that is why you can see that both the models are giving me different outputs. So this is a simple implementation using TensorFlow Keras. When you are doing it for a particular problem, you can use your data, you can add, subtract layers, and accordingly you can train your model and predict the output. So thank you for listening. I'm open for questions now. If anybody has any questions, you're most welcome. If you have any questions, you can type it in the QA section. So we have gone through what sequential data is. Yes, so Prabhakar wants to ask a question. Prabhakar, you can please type it in the QA section. In the QA section, you can type the question and I'll be happy to answer you. So Prabhakar, you have raised your hand. If you want to ask any question, please type it in the QA section. So I'll give quickly a quick recap of whatever we have done today. We talked about sequential data, where we saw that what sequential data is, what are the characteristics of sequential data. So simply we can define sequential data as any kind of data in which the order is important and each of the input is dependent upon each other. The examples of sequential data could be textual data, time series data, video data, all these audio signals, all these are examples of sequential data. Then when the sequential data, since it has some special characteristics where order is important and the timeline is important, we need some special networks for sequential data. So whenever we need to analyze or we want to process this sequential data, the two most common models are RNN, which is recurrent neural network, and LSTM. Okay, so Prabhakar says he's trying programming language conversion. Give some tips. Okay. So whenever you are doing programming language conversion, it will be a many to many problem. And when we talk of this many to many problem, that means you will have to use a network which has many input layers and many output layers, and you will have to train it rigorously so that when you give a sequence of text you will get another sequence of output only. So that is important. And for using some specific network, if you want to try some specific network, so in this case LSTM will work better, and there are a lot of new variants of LSTM that have come up. So if you try and search the latest research papers related to LSTM, you will find a lot of work has been done in this area, and you can use any of the latest LSTM variants. There you might get success in program language conversion. So transformer is okay, but when if you're just doing the translation, we can say transformer is an advanced version of this only, where you will have the attention mechanism also. So in your case, if you just want to convert the keywords, like if you're talking of any programming language that you are converting, or you are converting some language, the conversion that you want to do is for some programming language or for some particular, like English to French or something like that. If you're doing it for programming language, then LSTM variants will work. But if you're doing it for a particular language, okay, programming language. So for programming language, this LSTM variants will also work good, because there you do not require much of the attention. Because there, if you follow just the same sequence in a programming language, the context will not be that important. As we speak English, Hindi, or any other language, there the context is important. But when we are talking of programming language, in that case, if I have a sequence of keywords, they will translate to another sequence of keywords only. So in that case, you can try some latest LSTM versions, they will work better. So if you will add attention and transformer, it will unnecessarily complicate the situation. Okay, Gunjan, you want to ask anything? You have raised your hand. Please type it in the QA section. So I hope, Prabhakar, I have answered your question. Can I get any trained model? So if you're talking of a specific programming language translation, then you will have to search for if there is any trained model available or not. Any like there might be people who have worked on it, and you can try searching on GitHub and other open source forums. There you might get. But any standard trained model I have not come across. But if you will try and search, you will find a lot of code on GitHub and other places where you can pick up that. Many times you will see people who are doing their research paper, they give the source code with it. And there are GitHub papers with code is a website where you will find such kind of papers and along with them the code. So there's a site paperswithcode.com. There also you can try. Not getting consistency, what to do? Okay, so which languages you are converting your, what language translation you are doing? From which language to which language? Okay, CPP to Rust. Okay, so actually, if you're not getting consistency, one of the major reasons is that the training of your model is not enough. And both the languages are quite different to each other. So when you're doing it to CPP to Rust, the training, I guess, in your case is a bit low, and you need to try on more data set, increase the input sequence also, try with different input sequence. Like currently, if you're using an input sequence of 4 or 5, try to do it in a longer way. Try to give 10 or 15 or something. And also, you can give the input about the special characteristics, like in CPP, if you tell them that a termination will come with a semicolon and things like that in your vocab itself, that might improve the consistency. So those are some of the tips that I can give. It's up to you how you have developed the model. But try on different input sequences, you might get some better results. So Prabhakar, I will give my mail ID over here. You can discuss it separately with me if you want to discuss further. I am writing down my mail ID in the QA section. In case you want any further discussion, we can do it one on one, right? Any other questions from anyone? So because we have limited time, you can send me a mail and you can send me your queries. If I'll be able to help you, I'll be happy to help. Okay, any other questions? Okay, no more questions. Then thanks, and thank you for listening. Thank you to the organizers for giving me a chance to talk to all of you. Thanks a lot.
Thank you, Akansha ma'am. You explained LSTM and RNN very well. Thank you for knowledge sharing. Thanks for the
Okay,
connect.
thank you. Bye.
Dear participants, just wait. We'll be starting the next session soon.